antennas. These antennas are being fed or connected by transmission line. This PCB, you know PCB, right? Printed circuit board. On this PCB, there are printed lines that carry the energy from the source to the radiator, to the antenna. So these are transmission lines, printed lines, and we need to understand how the wave propagates over this transmission line. So this chapter is about transmission lines that carry high frequency signal or RF signal, radio frequency, which is needed for wireless communication. And all the communication we see is based on using transmission line. So this is the basic circuit, or this is the fundamental circuit. So we have a generator, signal source, usually RF high frequency signal source, power source, and some generator impedance, source impedance. Then we have transmission line. The transmission line can take any different shapes, and we have different transmission line. Then we have on the receiver side, we have the loop or the impedance. This transmission line carry high frequency signal. Normally high frequency signal. It can be coaxial line. You know the coaxial line you use in your house for the TV receiver? Yeah. This coaxial line has inner conductor and outer conductor. It's good for high frequency. It could be two wires line. This is an old-fashioned. It is good for lower frequency, below 1 gigahertz. Below 1 gigahertz is good lines, but for higher frequency, higher than 1 gigahertz, this line become highly lossy. So the power will lose its energy along this line. This line is better for high frequency, and it creates low loss actually. So this is a basic circuit. We have other types of transmission line that we will see throughout this course. We have the two parallel wires, as I explained. These are two parallel wires. And we have coaxial line, we have microstrip line. Microstrip line is the lines printed on PCB, on printed circuit board. You know your motherboard on the computer? Yes. It has some lines. These are called the microstrip lines. And we have optical fiber, waveguide. These are different categories or different types of transmission line. Looking at this circuit, we have a transmission line that takes the energy from the source to the load. The load happens to be RC. Can be anything. Which one is 2? Which option is 2? Please don't have the finger. So VA prime, this is the voltage here at the generator, and this is the voltage at the receiver or at the loop. Are they equal? Which one was A? Which one chose A? B? No. C? So the guys who choose C, why choose C?
Depends on the.
The answer is C. The answer is could be yes or no. The answer could be A or B. Depends on. The answer is C. This voltage could be equal to this voltage or could be not. Based on what? Based on what, Shabab? What's your name?
Ahmed Khalifa.
Muhammad.
Depends on the transmission line's length and impedance.
Lose answer. Not specific. I need the main reason. Please.
The transmission lines, if it's have resistance, or so the voltage will drop or not.
Depending on the resistor?
Yeah, of the transmission lines, maybe.
No, not exactly. Yes.
If it have inductance, the phase will change.
What else? Yes.
Depending on the frequency.
Depending on the frequency of the signal. Depending on the frequency of the source. In EE201 in circuit source, it was always this guy equal to this guy, right? Yes. This was the case. Why? Because this was either DC or low frequency signal. Like the power, the electricity is 60 hertz. It's very low frequency. And for lower frequency, it's okay to say these two guys are equal. But for higher frequency, it's different story. Okay? So the answer, it does depend on the frequency of the source, or more specifically, it does depend on the ratio L over lambda. Some of you said the length, but the exact answer is L over lambda. L is the length of the transmission line. So based on the ratio L over lambda, lambda is the frequency. Lambda, what is lambda in terms of frequency? Lambda is V over F, the wave velocity over frequency, right?
Yes.
So it based on the ratio L over lambda or L over U V over F. At the end of the day, it's more more focused on the frequency. The frequency of the signal will tell us if these together equal or not. Still not clear. So what is the good frequency that can allow us to say this together equal, or what is the bad frequency that says this together not equal? Now what is the good frequency? What is the frequency limits, or what is the wavelength limits to answer this question? Okay, so let's look at the circuit again. Assuming the voltage here, Vg, the generator, equal to this cosine wave, V0 cosine omega t. This is the voltage here. When this voltage travels along the line and reaches here, what is the new voltage? Is it the same time? It will be later, after some time. So assuming the time here is 0. The time here is 0. So it will reach here after some delay time. How much is the delay time? How long is the delay time? How long is the wave will take to travel from here to here? Time. Speed over distance, right? So the time delay is the speed of the wave over the distance. Assuming the speed is the wave of light, is the speed of light. So at this point, the voltage is cosine omega t. At the other point, at point B, it will drop, the time will reduce by the delay time L over C, right? Okay, Shabab, L over C is delay time. Assuming the wave is traveling by the speed of light. By the way, it could be plus or negative, it doesn't matter. It could be plus or negative, because I will assume t equal to 0. And assume t equal to 0, so plus or negative doesn't matter. So the wave will go from here to here after some delay time equal to distance over velocity, which is L over C. So this is the new voltage at the load end. It does have a phase delay. So this is the voltage at the transmitter, no phase. When it reaches to the receiver, to the load, it will have a phase equal to phi 0. How much is this phase? What is phi 0 here? Omega L over C.
Yes.
Right? So the phase delay here, the phase difference between the two signals is omega L over C. Now let's take some example, some specific example. Assuming t equal to 0 in this equation, assume t equal to 0 and the frequency is 1 kilohertz. 1 kilohertz is not big frequency. Okay? So reasonably high frequency. Assuming L under this values, assuming at t equal to 0 and the frequency 1 kilohertz, assuming the line has a length of 5 centimeters. What is the voltage VDB? Just substitute t equal to 0, phi 0 omega L over C. The answer is the magnitude of the voltage is 0.999 VZ. This is the voltage at the load. What was the voltage at the transmitter, at the cell generator? It was V0, V0 cosine 0. So the voltage dropped by how much? How much is the drop heavy? Something 0.00000, something we can't ignore. So for this length, for 5 centimeter, at this frequency, the two voltages are almost the same. Okay? For when the line is only 5 centimeter at 1 kilohertz, the two guys are very similar. What about if the line becomes 20 kilometers? Like phone line, like the landline, the land phone line. So you are receiving signal for the landline from Jubail, from Dammam. So for L equal to 20 kilometers, what will be the new voltage? Substitute here. You have LC, T equal to 0. The new voltage here will be 0.91 V0. So it drop by how much? How much is the drop we have here?
0.9.
9%. Drop by 9%. Here it was V0. V0 at the generator. Then after 20 kilometers, it will drop by 9%, which is good, which is big. So the answer could be yes or no. The answer could be yes. The two guys are the same if the length of the line is only 5 centimeters at 1 kilohertz. But if the length is 20 kilometers at the same frequency, 1 kilohertz, it will drop by 9%. So the answer could be yes or no, based on the length of the line and the frequency of the line. In this notes sometimes arrive, if you go out of this slideshow, you will see notes down. You see these notes, you write some notes here, so try to read this. What about, let me finish. So we have now studied two cases, when L is 5 centimeter or L is 20 kilometer. We have found that as L gets bigger, we have to consider this transmission line has effect, is not short circuit now. The transmission line is not short circuit as you thought in EE 201 or 213. This transmission line is alone. We need to see what do we have here in this transmission line to cause this voltage drop. If you take, and let's go back to L equal to 5 centimeter. Assuming L is 5 centimeter and the frequency instead of 1 kilohertz becomes 1.5 gigahertz. So same length, 5 centimeter. At 1 kilohertz, the voltage, the two voltages are almost the same. Now the frequency becomes 1.5. What is VZ? What is VBB? Calculate, right. I told you to bring Karasa. What is your Karasa? I told you to bring Karasa. Who doesn't have because I will keep you absent. Bring Karasa next time.
Inshallah.
So tell me what is VBB if the frequency is 1.5 gigahertz. I don't need calculator, we can do it by hand. So assuming the line has 5 centimeter and the frequency 1.5 gigahertz. What is VA? A prime is VZ. Okay? All of this when T equal to 0. So what is VBB? What is V at the load? Just resolve the question very easy. شباب what is VBB? What is V at the generator? When the frequency 1.5 gigahertz? No. Just substitute T equal to 0 and define 0 omega L over C. Okay, omega 2 by F, L over C, L is given, C is given. Did you do it? You will have Karasa? What is VBB يا شباب؟ Okay, what's it? Why it is taking that long? So it's V0 cosine what? 2 by F omega L over C. L is 5 centimeter, right? Over C is 3 times 10 power 8.
1?
F is 1.5 gigahertz.
1?
So what is the answer? Not 1. It's like V0 cosine by over 2. If you do this stuff, you will be cosine by over 2, which is what? Which is 0. So this, again, it's not large distance, not long transmission line, but the frequency is different. And now you have no voltage as a load. Okay? So this is extreme case. In case the frequency, in case this guy was 1 kilohertz, when this guy was 1 kilohertz, 1 kilohertz gives you the voltage at the load to be 0.99 VZ, very close to the voltage. But when the frequency changes, it is 0, no voltage here. Okay? This is because of the frequency, as I said. So the frequency is the major parameter here that control the wave received at the load. So we need to understand what is going on here and what caused all this effect of the transmission line. Okay, this is the role of the wavelength. Wavelength means frequency. Okay, Shabab? So the main parameter here is a phase created by the length of the transmission line, and this phase is omega L over C, which is the parameter here, omega L over C. At the end, omega L 2 by F L, C is lambda F, it will be 2 by L over lambda. So the ratio L over lambda is the main parameter. If L over lambda is very small, the two guys will be the same, very simple. If L over lambda is smaller, very small means less than 0.01. Okay, so the threshold is that if L over lambda less than 0.01, then we can say that VEA equal to VB. If this ratio is very small. Bigger than this, no, it's different. You have to do the math. It will be different. Okay? VBB will, the voltage here will be less than the generator voltage if this ratio is bigger than 0.01. Does this make sense, يا شباب? Huh? So, can you tell me what is going on here? يعني, generally speaking, we are expecting to have a voltage at the source, at the load, less than the generator voltage. Why? That
Because of the heat losses in the wires.
because of the loss in the wire. This wire has resistance, right? This wire has some resistance here. How much is the resistance? What's the resistance of this part? It is not physical resistance, but it is effective resistance.
VO.
It is rho L over A, I guess, right?
Mhm.
High school resistance. So it does have resistance. What else it does have? And what other than resistance? This resistance will absorb some energy. So are expected to receive less voltage here.
Inductance.
All of this because of the frequency. It does have inductance. In addition to this, it has some inductance. Why it does have inductance? L. So it does have R, it does have L. Why it does have L? Current carrying wire would generate a
Magnetic field.
magnetic field. Any current carrying wire, and with the frequency, you will have more magnetic field. Am I right? So we do have inductance. Again, it's not physical inductance. It's not like this. This is physical parameter. This is effective parameter. It has effect. So it does have R, it does have L. What else it does have? Does have, where is the capacitance? These two guys, these two wires like this, right? So do we have capacitance here somewhere?
Inside the wire.
Here, we have capacitance here. So it does have R that absorbs the heat. It does have inductance that create magnetic field. It does have capacitance. Why it does have capacitance? Two conductor with air gap. It's capacitance. With high frequency, these effects are highly powerful at high frequency. The more the frequency, the more effect we have from these guys. You cannot ignore them. Yes.
According to the final equation, the final effect is only a phase shift. There is no loss, nothing. It's just a phase lift.
Yes, it is phase shift, but when you take the cosine of this phase shift, it will give you a number less than 1. Right? Cosine of the phase will drop
So we
from
cannot
1 to
say.
minus 1. Hmm?
So we cannot say it is loss. In fact, it is only a phase shift. A delay.
Phase shift will create loss, what's your name?
Double.
Abdullah, when the phase is here inside the cosine.
So,
So the cosine will be less than 1. Am I right? Or more than 1? Cosine anything between minus 1 to 1. So this cosine will give you a number less than 1 times V0, so it will drop and V0. So the phase shift will create some kind of loss. Are you getting this?
بس إن هذا البيهيفير حق الكوساين حتى في الفانكشن الأساسية بالجنريتور
Uh,
في بيصير بين السالب 1 والواحد.
yes, but when you add the phase shift, this will drop further. The cosine will give you lower value. When t equal to 0, this 1. When t equal to 0 and you have any parameter here, it will give you a number less than 1. So the loss is always 0. The loss is always 0. And this is the best. This could be the best case with 999 VC. So as we said, we need to understand what is going on here. We said we have R because any piece of wire has some resistance. We have inductance because we have magnetic field. We have capacitance because there is electric field here, two conductor, air gap. What else we have? So we have R LC. We have R LC. What else we have? What is the fourth thing you have here? The effect of the transmission line.
Reflection.
I will come to this later. We have reflection, but I'm talking about circuit element. In addition to our LC, we have other element here that affect the wave propagation. This transmission line is composed of two pieces, right? Two things, which are what? This transmission line, two wires, and in between we have
Air gap.
the electric. It could be air, it could be plastic, could be something else, could be anything. So these are two pieces, conductor, and in between some dielectric, some insulating material. It was like two wire coaxial line The line you have in your TV for receiver, it is not air. Between the two conductors you have plastic, right?
Yes.
You have some dielectric.
Yes.
Does this has effect? Does this have effect? It does. We have here some kind of sorry. Next. Anyone has tissue يا شباب? Or it dries. Sometimes you get over and you stick. So as we said, we have here, we have R and we have L and we have C capacitance. Here we have some kind of material, which usually is not air. It's not air. It's air only because of simple example. This material will absorb some of the energy, right? It's a physical material. This absorption will be modeled as G. What is G here? Conductance, 1 over R, like conductivity. You know, the sigma, 1 over R, is something like conductivity. The more the G, the more the loss we have in the dielectric. Okay, so the wave will lose some of the energy over the wires and in the dielectric. This will absorb some of the energy. The more the frequency, the more the loss we have. G is proportional to يعني G, this G يا شباب. Is this? So again, we have R, we have L, we have C, and we have something here we call G. G of the dielectric is proportional to sigma.
Is the same as the core losses?
What?
The core losses.
Core losses? You mean the magnetic core? The core of the transformer?
I think it's.
It could be, because there's some similarity. Because the core absorbs some of the magnetic field. Is this what you mean? If this is the core of a transformer. So this G get increased by its conductivity. يعني we are assuming we have dielectric here. The dielectric, if it is good dielectric, it will have sigma equal to 0. If sigma equal to 0, you will have no G. But if sigma gets higher, you will have G, and G is the conductor will absorb some of the energy. So you are losing some of the energy. Anyway, so it's not simple, it's not short circuit. This guy is not short circuit, and these two guys are not equal. Okay, generally these two guys are not equal. This is introduction. Now we have two types of transmission line. We have something called non-dispersive and dispersive. What is the meaning of this? Dispersive means distortion transmission line. It will cause distortion to the wave. So look here, I have here a simple transmission line. If the input very similar to the output, it's distortionless. لا تشتت. You call dispersionless. Dispersion means distortion. If you have short transmission line, look at these two guys. Are they same? Are they different? Are they similar? No. Different. This distortion, short dispersive transmission line. Short transmission line, dispersive means it causes the signal to get distorted. This guy is similar to this but longer. So this is long dispersive line. Look at the two guys. Highly different. So when it was short, it is slightly different. Now it's highly different. So this guy is distortionless or dispersionless. This short dispersive, long dispersive transmission line. What caused this effect? Yeah, what caused this effect? This effect is caused by the characteristic of the transmission line. The material, the dielectric, and the structure of the transmission line. A dispersive transmission line is one in which the wave velocity is not constant as a function of frequency. So, generally speaking, any periodic waveform, assuming you have like a pulse square wave, how many frequencies we have there? Assuming you have like square wave like this, how many frequencies we have here?
Many.
Can I write this wave, this function f of x whatever, as a series? Can I write it as a series of cosine and sine
Yes.
using
Fourier.
Fourier series, right?
Fourier series.
Fourier series will give you cosine plus cosine plus cosine, and each one has different frequency. You will have like something like this: cosine omega 1 t plus some phi plus another cosine, not omega 1, omega 2. Omega 2 means different frequency. T plus another phase and so on. So you have يعني, many frequencies. If all these frequencies travel with the same wave velocity, so the transmission line is distortionless. If these frequencies travel with different velocity, you will have distortion. You will have distortion means you will have this case or this case. Again, if all the frequencies travel with the same velocity, you will have this case. If these frequencies travel with different velocity, you will have the distortion case. Clear? I assume it's not clear. We will cover this in more details in section 2.6. We're now in section 2.1. We will have more deeper, we'll go deeper in this. Okay. Now we need to speak about something called propagation modes. Propagation modes means how as we said before, based on Faraday's law and Ampere's law, a time varying magnetic field would produce what? Time varying magnetic field would produce time varying electric field. And time varying this is based on what? Faraday's or Ampere? Time varying magnetic field produce time varying electric field. This is Faraday's law or Ampere's law?
Faraday's.
This is Faraday's law. Okay, Ampere's law said the other thing. Time varying electric field would produce time varying magnetic field. They are stuck together, you can't separate them. Once the field is time varying, one of them must produce the other one. Other than this, you cannot use your phone, no communication. If the two guys are not stuck together, the time varying electric field and the time varying magnetic field, if they are not stuck, we have no communication, we have nothing, we have no tablet, nothing. Okay? This is the reason we call it electromagnetic field. They are together. You know the coin has two faces, you can't split them. The same as time varying electric field and time varying magnetic field. So basically, they are, when you receive a signal on your phone, this signal is coming to you like this. So the electric field is directed along, say, y axis, and the magnetic field is directed along z axis. So E, at any time, E is a vector along y. B or H is along z, and they are propagating along x. So E in some direction, H is perpendicular to E, and both of them are forming a plane. This is called a plane wave. This is what is happening, that E is always in some direction, H or B perpendicular. This is called like plane. Now we have plane of two vectors with angle 90 degrees. This plane is moving along X. So they are always like this. They are always like this. X, Y, Z. One of them X, one the other in Y, and the third will be the propagation direction. How do I know that the propagation is X or negative X? And how do I know whether it is propagating in X or negative X?
Right hand rule.
Right hand rule. What does this mean? Look at the direction of E. This is how communication takes place. The signal you are receiving has some component E in Y direction, another component in Z, and both of them like plane wave. E and H exist in one plane. And this plane is moving in a third normal direction. And the propagation should be perpendicular to the plane containing E and H, or E and B. And the direction of the propagation, اللي هو هنا X, is based on the right hand rule. Look here. Assuming E is this green guy, H is this green guy, 90 degree, use the right hand rule. So E cross H is the propagation direction. Okay? It's not the opposite. You have to use like E cross H. E cross H, right hand rule is K is the propagation direction. It's always like this. So when you get confused, you must use the right hand rule. This is the nature of communication. This is how communication takes place. This kind of propagation is called TEM wave. What's the meaning of TEM? Transverse electromagnetic field. Transverse electromagnetic field. What does this mean? E and H are perpendicular to the direction of propagation. Do you see any E component in electric field in the direction of propagation? Yeah, do you see E or H? B, B is H. Do you see E or B in the direction of X? It will never happen. Okay? It will never happen that you see E or B in the direction of X. It's always the electric field in Y direction be in the normal direction, and both of them are one plane perpendicular to the direction of propagation. This configuration is called a, what's the meaning of this? Transverse circumagnetic. Transverse circumagnetic. There is no E nor H in the direction of propagation. Okay, Sharon, clear? So the wave, assuming the wave is propagating along this direction. So E will be always like this or like this. H like this or like this. You will never have E or H in direction of propagation. Okay, this is how communication takes place. It happens to be like this. And this is how the antenna send the electromagnetic waves. And you have frequency omega and all this stuff. Is this clear? This propagation mode. It's propagation mode. All these transmission lines, all these lines are TM. Yeah, this coaxial line, the line you have in your house, the line for your TV receiver. It does allow the propagation mode is TM. Again, E and H are perpendicular, and E, H like this, and both of them are moving like one plane in direction of propagation. So this has TM. These two wires, the old-fashioned receiver cable, again it's TM. This called barrel plate lines. So two lines, barrel with some dielectric. It does support TM. This is dielectric strip line, macro strip lines, like the lines of your motherboard or PCB printed circuit board. This is called coplanar waveguide. So you have a line in the middle and the two lines like ground plane. The two lines like supporting the waves. All of this are supporting TM. Yeah, the wave propagating will be transverse magnetic field as we explained. We have some other higher order transmission line, like this, we call it waveguide. You know what is a waveguide? It's like metallic hollow tube, metallic tube. ماسورة معدنية مجوفة. And the wave propagates inside this hollow tube. It does, this is very good for much higher frequency. For space communication, telecommunication, we like to use waveguide. And this is concentric dielectric layer, like two fiber optic, you know, the fiber cable, like two dielectric concentric. This is called higher order. It supports other mode of propagation that we'll cover later in chapter 8. But so far, we will focus on the transmission line that support what we call transverse electromagnetic field, where E and H like this. E is some direction, H is normal, and both of them using the right hand rule, this plane is moving in K direction. Okay, Shahad? Let's try to understand this. Assuming you have a source, this source is like the dish in your house. You have dish, right? Receiver. This is a dish, and this is your television. And you are connecting the source, the dish. Dish receives the signal by coaxial line. Coaxial line has inner conductor and outer conductor. You know this coaxial line, right? From 305. So if you look inside the coaxial line, what is the direction of E and H? What is the direction of E and H? We have two conductors, right?
Yes.
So E is perpendicular from the inner to the outer, this direction of E. And you have current carrying wire. This guy in the middle carrying some current. So you will have magnetic field, right? Right hand rule. So the magnetic field is the green one. So the red one is electric field. The green guys, the circles are magnetic field. Does this make sense? It makes sense. You have two conductors, electric field in between, and the magnetic field surrounding the inner one. The magnetic field happens to be clockwise. What is the propagation direction? This electromagnetic field is propagating in or out of the pitch. Again, E cross H will give you propagation where?
I think.
Huh? What's the name? Abdal, in or out?
I think it's radial.
No, radial is the E, is the red line, because the red line we call it radial in R direction. This direction يا شباب, this direction is called the radial direction, in R direction. So the radial is this guy. This is the green is we call it azimuthal. Okay, so assuming the green is the magnetic field is clockwise. This is electric field. So using E cross H, the propagation will be in or out?
In.
Huh?
In.
In how? So E cross H. We said this is E. E is the red, green, this guy. So E cross H will be this E and this H. So you should kill this direction. It will not be like this. It will be like this. Propagation will be in the page. Again, okay? Is this clear? E cross H. E cross H is K. E cross H is K direction. there is a reason for this, but it's beyond this also. That E cross H will give you some direction. This is the direction of propagation. So take the cross product of this guy, will give you a direction, which is the propagation direction. Okay, Shabab? Does this make sense? Yes.
When you say propagation direction, you mean the current direction?
Not the current, the wave direction.
The wave?
Not the wave direction. Yes. The wave direction. The wave travels by the speed of light. Okay, current is here only, but the wave is propagating in the dielectric. In fact, the current is out of the page. Where is the current direction here? Where is the current in the inner conductor? In or out? Out, because the magnetic field will be in also. In. The current is in also. Okay? And the propagation direction is in also. So both of them are the same. So here the current is the inner conductor in the same direction of this magnetic field. But the current in the outer is opposite to this guy. Are you getting this? The current in the outer conductor is opposite to this. Like any two lines, يعني when you have two lines, this carries current this way, the other must go back, right? So they are opposite to each other. The current here opposite to this guy. But it happens here that the inner conductor is the same direction of the wave propagation. Okay, or it should be the case like this for this example. The current direction, the same direction of the wave propagation. Okay, Shabab?
Yes.
Everyone wrote his name in this thing. So this is a transmission. This is what we said. This is the whole story is here. The whole chapter in this slide. So this is a transmission line. Look at the transmission line. I will cut this line into pieces. Okay? Each piece will have a length of delta Z, which is close to 0. I will divide piece. Each piece has a length of delta Z. In each delta Z, we call it differential section. Differential sections, each has delta Z long. Each delta Z, each part of this transmission line contains effective elements, which is R, L, C, G. Why we have these elements? Because of the frequency is higher. Because L over lambda, you remember L over lambda is bigger than some value 0.01. So it's not our choice. You are forced to deal with these elements. Okay? R is the loss, the heat loss. L is representation of the magnetic field. In a current can have magnetic field. C is the capacitance between the two guys. G is the conductance of the dielectric here between the two conductors. G is the conductance of the dielectric between these two guys. It is not air. Dielectric usually not air. Okay, simple case we can assume air, but generally it's not air. It's like plastic or some dielectric. These are effective elements. The per unit length. Yeah, R here is the resistance per unit length, ohm per meter. So R times delta Z is the resistance of this guy. L inductance per unit length. Conductance per unit length, capacitance per unit length. Okay, Shabab? This is called the Lambert element model. So we are using Lambert element, this Lambert element model. Okay? Each element is Lambert element. This is a table that we will cover more details about this. So for each line, we have 3 lines. We have a coaxial line, 2 wires in dielectric, and we have a parallel plate line, 2 conductors with dielectric. For each line, we have some values that has been proven experimentally. We have R, L, C, G. In each line, they have calculated R, L, C, G. Remember, R dash here is ohm per meter. R dash times Z. So R is the resistance per unit meter, per unit length. L inductance per unit length, and so on. So the values here, this are L, C, G. Look here, what are the parameters we have here? For coaxial line, assuming the inner conductor has a radius of A and outer radius of B. So R dash is defined as Rs over 2 by 1 over A plus 1 over B. Rs is called the surface impedance equal to some constant value. Rs is defined as root by frequency. Look at the frequency. The more the frequency, the more the resistance. Look at the frequency here. Mu C is mu of the conductor Mu C is mu of the conductor, which equal to what? What is mu of a good conductor? Mu is the permeability. It's magnetic field ratio, B equal to mu H. Mu is same as mu 0, same as mu of air. And all this material has permeability equal to air, mu 0, 4 pi times 10 power minus 7. Sigma C is sigma of the conductor. Okay? This equation is very important. Yeah, this equation is very important to understand the behavior of this transmission line. Now look at this RS, يا شباب. If the frequency gets higher, RS gets higher or lower? Higher. So more loss, you will lose more power. If sigma C is sigma of the conductor. If sigma C gets higher, the RS gets higher or lower? Lower. In fact, if sigma C is infinity, what is the value of RS? Zero. There's no resistance. And if the transmission line has a very good conductor, infinity conductivity, excellent conductor, it will have no loss. R0. Okay? Because this comes from the resistivity. Rho is 1 over sigma, rho L over A. So what this is called perfect conductor. If the conductivity of any conductor is infinity, it's perfect conductor. Okay, شباب? So we can make sense of these parameters. You don't need to memorize this, but try to understand the relation between this parameter and our LCG. L is mu over 2 pi ln B over A. Remember, BA is the size of the outer and inner conductor, 2B and 2A. So this L. G, look at G. What is G? The conductance of the material between the two conductors. You have two conductors. You have dielectric in between. This dielectric will absorb some of the energy. This conductance equal to pi sigma over ln B over A. How can I bring this down? I need to bring this down to get rid of this conductance. How can I bring this value down? If sigma equal to 0, if you have 0 sigma means what? What's the meaning of 0 sigma? Good conductor, good dielectric, no conductivity. A dielectric means insulator, no conductivity. Usually it's not the case. يعني any material around you, this material wood is dielectric. Does this mean the conductivity is 0?
No.
It's 0.0001. It's not 0. But if you can make it 0, you will have no power loss here. If the waves go in this piece of wood, it will lose no power. If it has sigma equal to 0. And if the dielectric between, you have transmission line and you have dielectric, if this dielectric has no conductivity, it will absorb no energy of the line from the wave. Okay? And in this case, we call it perfect dielectric. Dielectric, excellent. Okay, شباب? This is what you did today is like introduction to transmission lines. We didn't start the business yet. The business will start next time. So here, to summarize, if you have perfect conductor, we said the transmission line is two pieces, two conductor and dielectric. For the conductor part, if it is perfect, this means it has infinity conductivity, and or high conductivity such that this value will be much less than 1. So RS will be 0. RS is the resistance of this conductor is almost 0 if it is perfect, if it has 0 infinity conductivity. The other part of the transmission line is the plastic in between, the dielectric. If this dielectric, if the material separating the inner and outer conductor is perfect dielectric, what's the meaning of perfect dielectric? No conductivity, sigma equal to 0, G will be 0. So we have two parameters that we can control, R, the resistance, and the conductance. If you can have good conductor, you will have no RS, no heat loss. If you have good dielectric, you will have no conductance, no power loss in the dielectric. And in this case, the new transmission line, and if you get rid of R and G, the new line is called lossless transmission line. This line has no loss. We cannot get rid of L and C. We cannot get rid of this. Okay? L and C is always here. But you can get rid of R if you have good conductor. You can get rid of G. We have G here, like resistance. You can get rid if you have good dielectric. This is the simple case, lossless transmission line. Thank you.